around yourself. To have a dynamics, you need to perturb the flow, you need to disturb the flow, you need to externally drive the flow, right? Then only you can see that there is going to be a dynamics. But if you have active system, as the name suggests, they are active, they themselves can generate flows. For example, if you think about a bacteria, if bacteria is swimming in a flow, it will disturb the flow around it, right? You don't need to provide the disturbance externally. The other idea is like, if, for example, if you consider ourselves, if we are swimming in a pool or in a river or any quiescent water body, will disturb the flow, and then the flow will be generated out of it, right? So when you have a system where activity is coming from the agent itself rather than the activity, disturbances are being generated by an external flow, or like if you look at Navier-Stokes equation, we had talked about two kind of forcing. One is body force, the other one is through boundary force. If those things are missing, and and flow is being generated. Thank you. I think this much should be enough. I will just, you can, yeah. And flow is generated due to activity of the agent itself. In those limits, we say that there is activity in the system, and if a flow is going to be generated, then we say that the flow is going to be active flow. Okay, so there are two ways to look at the system. So here I have taken few examples. So this is a suspension of sperms, and you can see sperms are motile in nature. So basically when they move around, they will generate the flow around it. Okay, and these are the simply the tracks of it, and what one can do, one can construct a vorticity field out of it, and this is how the vorticity field is going to look like. Okay, and again you can see that if you think about any active agent, like if you think about bacteria or any such thing, they move, if you think about it, it will move randomly, right? There is no way that they should try to move together. But if you look at this plot, you can see that they start to form regular structure. Okay, regular structure, I mean they start to form like vertical structures and all, right? It's not a random in that spirit. Okay, the structures here are pretty large. So here this length scale is 50 microns. Usually the size of bacteria or sperm is going to be of the order of few microns. No, it is not me. Okay, I guess it's fine. It was me. Same. Okay, no, so speaker was on for this. So okay, all good. Fine. But it took quite some time to show up. I mean the worst thing. Okay, so here if you look at this bar, the length scale, that length scale is going to be 50 microns, and you can see and if you think about the agents, they are going to be much smaller, like somewhere here, right? Much smaller than these length scales. And if you look at the structure, these structures are going to be much greater than that, right? So there is no way to, means you should expect that they are going to form these structures. Okay, so what we'll try to do, we'll try to understand, not understand, basically we'll try to write down the governing equation, and then we'll try to see how can we describe it, and what are the meaning of these structures, and can we try to use the same analysis that we are going to learn and try to understand these systems as well. Okay, so this is one example. Here these sperms, they are moving in a fluid. Okay, so you can easily see that there is a flow around it. But what happens to this system? Can anyone tell? Of course it says sheep herd, right? So what do you think of this? It's pretty regular, right? You can think about the structure, it's pretty regular, and if you, so you can see what is happening here. They are trying to go through this narrow path, right? Narrow gate, and what happens, it's like a fluid, right? If you try to push a flow through this gate, this is how it is going to be, right? Because of mass conservation and all continuity equation, right? So this is very similar to it. So this is one structure where I'm trying to convince you that if you take these active agents and if you try to look at the dynamics is going to be very similar to a flow that we have already seen. Okay, there could be these sheep, they also tend to form like, you know, circular structure, vertical structure, it has been observed, and these the features are going to be very similar to what you see in a fluid flow. Okay, so this is one example. The other example is when you have, these are like, this video I'm pretty sure you might have seen many times, and these are you know, starling birds, and what they are doing. So if you, so the number of birds could be here up to thousands to maybe 10,000, right? And if you think about these birds individually, what will happen? They will move randomly. But if you look at a collection of them, you can see that they are moving like a, you can see that it's like a flow, right? They're like, if you look at there are coalescence, there are detachment, right? So it's like a drop which is trying to coalesce, a drop which is trying to detach, right? So it's pretty much like a flow field it is behaving. Also, if you look at the interfaces, so let's wait for some time. If you look at these interfaces, the interfaces, I mean, where there are birds and when there are no birds, right? That's how you will define the interface. If you look at the interfaces also appear to be very smooth, like a fluid flow. It should not be in that way, right? So what I'm trying to convince you here, that even for this system, the dynamics is going to appear very much like a flow for it, right? Even though, means, other than air, which is very thin, there will not be much, you know, interaction through the flow, right? So these systems are like dry systems, but still for this system, what you can do, you can write down an equation of motion, and the equation of motion will be very similar to means the origin of these equations is going to come from the Navier-Stokes equation. Okay, so of course these phenomena like sheep herd, this is bird flocking. If you watch enough National Geography or any such thing, you will see that there are many such behavior in animals, right? They try to move together, and so to describe these things, so these are simply known as flocking, herding, swarming, school, and other such behavior, right? So to describe, so basically this is the system that we are going to focus. We'll be focusing both on wet and also on dry system. Okay, and how to write down the equation. If you think about these guys, so individually these agents are moving randomly in the space, right? But when you look at the collection of them, you can see that they will try to move for certain times in a given direction. So the structures are going to be of the order of system size itself. For example, in this case, the structures are of the order of system size. Similarly, in the video that you have seen, in those cases, the structures are going to be of the order of system size, and the direction also is going to be, means it's going to be very coherent and again of the order of system size itself. Now, the question is, if you take these guys, okay, like sheep or any other things, if you add a constant velocity to all these guys, okay, then what will happen? It will, you know, the dynamics is, means it breaks symmetry immediately. Okay, how should I put it? I have not covered it. Okay, so how many of you know, means we have covered Navier-Stokes equation. So can how many of you know about Galilean invariance? Yeah, okay, you know. So basically what happens, if you take the system, if you put them in a frame of reference that is moving with a constant speed, your dynamics should not get affected, right? So that's what Galilean invariance says. Now, if you do for these systems, you will see that the system starts to break the symmetry immediately. Okay, so the dynamics will not be same. So if you take these birds or these sheep, if you add a constant speed to them, you will realize the dynamics is not going to be the same. So what I'm trying to say is, suppose there are these like sheep, they are moving in random direction. If you consider individual of them, they are going to move randomly, right? But when you bring them together, what happens? You will see your neighbor, and then you will try to align yourself, and then accordingly you will try to go in a certain direction. Either there will be a cue, or there will be this natural alignment. Okay, even if you think about a crowd, basically what you try to do usually, if it is a dense crowd, you will try to look around your neighbor and then you move accordingly, right? If you think about a railway station, or you know, at airport or any such setup, this is how it is going to be. Now in these cases, basically what you will try to do, you will try to move with the average velocity of your neighbors, right? But what if I provide you an external velocity, or what if I put you in a frame of reference where you have an added speed, which means there is a given direction and a slight velocity? Then what will happen? You will break the symmetry means you will not break the symmetry spontaneously. What was happening in these cases, like if you think about birds which are moving around, individually they were moving randomly, but all of a sudden they pick a direction and then they start to move. For example, in this video, so you can see that there is no reason that they should go in a given direction, right? They spontaneously break the symmetry and then they start to move in that direction, right? But if you give them a slight push, which means if you put them in a frame of reference which has certain velocity, then what will happen? It will not break the symmetry spontaneously. It will pick the direction in which the added boost is given to them, right? So that spontaneous symmetry breaking disappears immediately, which means that system is no more Galilean invariant, right? Whereas if you take your Navier-Stokes equation, if you do the same thing, you will see that your Navier-Stokes equation will be invariant under Galilean invariance. Okay, so this was an important point, and on the basis of this, what Toner and Tu did, they said what we can do, we can take our Navier-Stokes equation, we can break its Galilean invariance, and that equation should be able to describe all possible set of dynamics which govern this kind of motion, right? So they did not say it is going to specify only for birds or sheep or anything. They said the idea is simple. If there is a system which is breaking symmetry spontaneously, and by the argument that I had just made, means which was made by Toner and Tu, and means it is, yeah. So there, it is no more Galilean invariance. So mathematically, if you want to mimic such system, what you have to do, you have to simply say that I will take my Navier-Stokes equation, and since just give me a minute. So since the motion appears to be more like flow, so I will take my Navier-Stokes equation, I just need to break my Galilean invariance, and then that equation should be, in some form, be able to explain these dynamics, okay? That was the idea. That's what Toner and Tu did. Yes, you.
The point of Galilean invariance, you are saying if you add a constant velocity to all the sheep herds, the cooperative behavior disappears.
No, cooperative behavior will be there, but the spontaneous symmetry breaking disappears. So for example, in these birds, so for some time they're moving in this direction, sometimes they keep on changing the direction, right? So it is there is no reason when they are moving in the, in the space, they need to pick a given direction. There is no constraint for them. So they pick this direction spontaneously. So that's how it breaks the spontaneous rotational symmetry. Now, if you give an additional perturbation, if you say that I'm going to give them a boost, all of a sudden, since the rule is simple, that you will see your neighbors and then you will try to align yourself. If that's the idea, then there will not be spontaneous symmetry breaking, there will be a forced symmetry breaking. Okay, and that's how you break the Galilean. It means the system is not same anymore, and you break your Galilean invariance. Is the idea clear? I did not think that I will be discussing this, but yeah.
Maybe I add a comment here on one if I can. So basically, mathematically, it's very easy to see if you break Galilean invariance because you have a PD, it's a Navier-Stokes, and then you replace B with B plus a constant C times T, and you substitute the old B with this new B, it's called B tilde, and then if the PD that solves B tilde is exactly the same as the PD that solves B, the PD is invariant. And in fact, if you plug in the Navier-Stokes V
equal to V plus CT or something.
Or CT, because there is no term that is proportional to B and all the other terms, B always enters quadratically, basically then you're never gonna basically, the system is always invariant to this transformation. But when you have, for instance, in birds, because there is a force that is proportional to the winds, the drag force, right? Then it's you break it immediately physically. Yeah, that's I think an easier way to do it. Yeah.
Okay, so using that idea, so is there any question in terms of invariance, like Galilean invariance and all? Yeah.
In 2D, yesterday they told we have added another term minus alpha u to dissipate the energy at large length in Navier-Stokes. So will that?
Okay, I see. No, so that is. Okay, I see. So basically, if you think about Navier-Stokes equation, so there is no dissipation term to begin with. Of course, there will be effects at the boundary, But usually, if you think about bulk, the effects are not going to be there for 3-dimensional Navier-Stokes equation. But if you are going to deal with 2-dimensional Navier-Stokes equation, since there are going to be, so basically wherever you consider soap film or any such thing, either it will be moving against open surface, which means against air, or it is going to move. Suppose if it is oil water interface, it is going to move against some interface. So of course, if there is going to be a dynamics, there is going to be a lot of friction, because now the surface area is much more compared to the bulk itself, right? So in that way friction comes, and that equation is, you are right, that is not Galilean invariant. So 2D Navier-Stokes equation that we usually solve for numerics and that is able to explain the experiments, that is not Galilean invariant. But in the stricter sense, the Navier-Stokes equation that we wrote down, means all the slides that we have, that is going to be Galilean invariant. Okay, yeah. Okay, fine. So now, if you do, so basically what Toner and Tu said, let's take this system and write down Navier-Stokes equation and break the Galilean invariance. And if you and what are the possible ways to break the Galilean invariance? Of course, this is how should I put it? I mean, what they did means there are n number of ways to do that. What they did, they took a call that how I'm going to decide that which terms are going, means up to what limit I'm going to consider the, so for example, what they did, they said for the gradient of velocity, I'm going to go up to second order, right? For the velocity nonlinearity, in terms of nonlinearity, will be going up to cubic order, right? Will not be going beyond that. And if we keep these constraints, then let's see how many terms we can add to Navier-Stokes equation, keeping these keeping these ideas into account. So basically you take Navier-Stokes equation and you say, no, I'm going to add more terms to it, more possible terms to it, which physically makes sense, and then let's break the Galilean, let's see how the equation is going to appear. So if you think about what additional terms which are going to break the Galilean invariance, it is going to be, if you take your advection term and if you add a prefactor which is not 1, that is going to break your Galilean invariance, right? The second term that is going to come from the fact that you will have this del dot u term, which is again, so basically if you have incompressibility condition, this term disappears immediately. This term also disappears immediately. This term is just showing as there is a source and sink to energy, because this is divergence of energy, right? This term is simply either a linear drag or linear reinforcement to the system. This alpha u, and again, as I don't remember the name, he said this is going to break the Galilean invariance. Similarly, you can have a cubic term that is again going to break the Galilean invariance, and then you will have other high order term. So here for generality, we have also considered that compressibility into account, but whenever we are going to solve, we'll try to get rid of these additional terms. Okay, so when you take these things into account, this is how your generalized Navier-Stokes equation is going to come into picture. And what you have done, you have ignored the terms which are going to be cubic in gradient and fourth order in velocity. So we have kept the term which is second order in gradient and third order nonlinearity in velocity, and we have ignored the term which are third order in gradient and fourth order or higher in the velocity term. Okay, so this is the in a very general sense, you can take your Navier-Stokes equation, you can break Galilean invariance, and this is the equation that you are going to get. Okay, but each term, so but the thing is that you can see that the origin of this equation is very mathematical, right? The authors never said that which term is going to get connected to what activity. So now, but the thing is that this equation should be able to, I mean that's the hope, that this equation should be able to describe whatever the videos we have seen before. So whenever you have activity, can that dynamics be described with these equations? Okay, now it is job of the person who is going to use the equation how to do the mapping of these coefficients and these terms to the actual system you have in hand. Okay, so most commonly used setup is what you will say that I will try to, so you say that you take the advection, and if you use a lambda 0 which is greater than or less than 1, and based on that you will define whether it is going to be an puller, pusher, or extensile or contractile kind of system. This is you get rid of it immediately. You say that my flow is incompressible. Then again for energy you will say that I'm not going to consider there is going to be source or sink to energy. You get rid of this term. This is our standard. Okay, let's look at these two terms. So alpha u, depending on the sign, it will be either taking out energy like a linear drag, or it will be injecting energy to the system. And if your system is injecting energy to the system linearly, then of course there is going to be accumulation of the energy at large length scale, right? So what do you have to do? You have to make sure that you should have a term which high degree of nonlinearity with a negative sign. Okay, so basically this beta u cube, what it does, it makes sure that the energy remains it does not become unbounded. Okay, if beta is positive here, then it will make sure that your energy does not shoot up. So at large length scale there will not be any accumulation of energy. Then you have a standard pressure term like what we have in the Navier-Stokes equation. You have viscous term. Then again this term will disappear, because again whatever we are going to do, we are always going to be in the limit where we are talking about incompressible flow. Okay, this term will disappear, and then you have again this term which will again means it is like square root of the advection and all, will get it. So basically we are going to take into account this term, and we are going to play with lambda 0, and we'll drop all other terms. Okay, and that's what has been used to means very commonly that is the equation that has been used in the community. Okay, so one such example, I'll just try to see that if you solve these equations, what you are going to get. So if you take your incompressibility condition and you take Navier-Stokes equation with this additional contribution, so now you have an additional contribution that is lambda 0, alpha, beta, and rest of the terms are exactly same like Navier-Stokes equation. So okay, to begin with we had 8 additional terms, but now what we are going to do, we are only going to take into account 3 additional terms. Okay, we have terms like lambda 0, alpha, and beta. Now using this, so this is known as incompressible tonal 2 very commonly. Now if you take this equation and if you solve them numerically, what you are going to get at very small time scales, you will see that there are many small structures. Okay, but if you wait for long enough, you can see that there is going to be coarsening, and so basically in the background, means this work is by basically the group of Prasad Perlekar and his student Navdeep Rana. He's at TFR Hyderabad. He will be visiting for the conference, by the way, but I'm not sure whether he's going to talk about this or not. So, so basically, what you will see if you take this equation and if you solve it, basically there is going to be coarsening, and that's what you see when you think about herd or flock. Okay, to begin with, there will be many at the individual level there will be structures that will start to form, but if you wait long enough, you will see that herd formation will start to take place. If you think about bird flock or sheep herd or any school, that's how it is going to happen. There is going to be a transient when you put things together, but eventually there is going to be a collective motion, and there is going to be a big flocking kind of behavior that is going to emerge, and that's what has been observed if you solve these equations. Okay, so you see small scale structure, if you wait long enough, it grows, and eventually it becomes large, and if you wait long enough, you will see that the vortex size becomes of the order of system size itself. And that's what we had observed when we talked about the sheep herd, or when we talked about the flocking birds, right? We'll get back to the sperm case in a minute. Okay, so
so Anupam, here where is the injection of energy is where precisely?
This is
alpha,
alpha, and also through lambda 0.
Alpha is not a friction. Here is the activity. Okay.
So here, whatever the data that I'm going to show you from the numerics, alpha is always going to be used as a parameter that provides energy to the system. So yesterday what you saw for the 2D Navier-Stokes equation, you had a term like, you did not have this term, right? This term was missing. You had an alpha u, with alpha had a negative sign, right? So what it was doing, it was dissipating energy. And how did we convince ourselves? Because that's how it should happen, because there is going to be a strong friction, and that is the reason it is going to dissipate energy linearly, right? That's what we said. But now what we are saying, that to take into account flocking, you have to have alpha positive, and you will associate this with the flocking energy or any such thing. Still, it is to tell the truth, it is still debatable. Even I don't understand what alpha actually correspond to. Does it correspond to the small length scale or does it correspond to the large length scale? Okay.
So, but then the physics of this, where is basically the drag now is cubic.
Yeah, the drag is, so it is just to kill the energy in the system.
No, yeah, but I mean, but let's say for instance, I mean, it's
okay.
Beautiful because with symmetries you can recover these terms, but then we know the physics of drags for objects flying. It should be quadratic with the velocity proportional to the area of contact.
Right. No, but so basically, so what happens if you go from, in many cases, the drag suppose may be quadratic at the microscopic agents, but you put them in collection, the drag form may differ. Because there could be other advantages. Suppose if you move together, then the drag effective drag may go down. Okay.
Yeah. So now it's sort of hidden in this.
Yeah. So it is hidden in that. It is hidden. So that's what it says. Okay, that's what it says. So here again we're talking about a collection of them. So whatever happening in macroscope, so again you can see that it is not coming from the first principle, right? You're not doing like, you start from the microscopic scale and then you say that I'm going to do coarse graining and I will do renormalization theory and then eventually I'm going to get this, right? The idea is very different here, the way we have arrived here. Okay. Okay. Fair.
Is it safe to say that energy dissipates at the large scales rather than small scales?
No, energy is being, we'll come to energy dissipation. So, of course, viscous term is here, right? So, viscosity is there for sure, and that is dissipating energy at the small length scale. So, whenever we think about Navier-Stokes equation, and you all have studied the origin of viscosity, it is because of the shear, means whenever there are two layers, when they are moving against each other, there is going to be a viscous force, and that leads to, dissipation, and it is at the molecular level, right? It is at very small length scale. But what we are doing here, we are also adding a dissipation term, which is going to act at a much larger length scale. And the reason being, at least what I believe, which Mathieu will also agree, is that to make sure to arrest this guy, because this guy keep on adding energy to the system, it is all adding at all length scales, right? So we just keep on adding, then of course there will be condensation of energy at large length scale, and to arrest it you have to add a cubic term. Okay, that's how I see these things.
Wait, guys, as an exercise, do you know why the lambda 0 different than 1 breaks Galilean invariance?
So those who have done Navier-Stokes equation and Galilean, they should be able to tell, like, why if you move away from lambda 0 not equal to 1, Navier-Stokes equation breaks the symmetry. So basically what we are saying, that you get rid of these two terms, okay? You take these two in the left hand side and these two, and forget about the forcing, okay? And they take these two terms. Now, if lambda 0 equal to 1, you will see that it is Galilean invariant. But if you set lambda 0 not equal to 1, you will say that it breaks this Galilean invariance immediately.
So maybe just as an exercise, do it later. But basically, the speed you're gonna get if you do a transformation u that goes to, so you actually have to transform x that goes to x plus ct, where c is the speed of the new frame. If you do that, a C term pops up from dtu, and another one should pop up from u dot grad u, and if lambda 0 is 1, then they cancel out, otherwise not. You should do it as an exercise. It's very simple.
Okay, so this is how your frame of reference is going to change, and then if you do all the, so equations will appear exactly same for the Navier-Stokes equation, but for these equations you will see that there will be some additional term. So even one should always do it independently. So you can see that if you add only lambda 0 term, that is also going to contribute something. There will be Navier-Stokes plus something. Similarly, if you have alpha u, you will have the original equation plus something. Similarly, if you have beta u cube term or beta u squared u vector term, it is going to have the same equation plus some additional thing, okay? And that's how you say that, it is not invariant. The equations are not invariant under this transformation, okay? Now, what I want to ask is that you look at these two images. On the left hand side, you have bacterial suspension which is moving in a nutrient flow. And on the right hand side there are this is a famous site in Mecca where you can see that people are moving in circles. So this is also the reason why I wanted to show that if you think about human, basically there is no way, means we are agents, we can move around the way we like, right? But here in this example you can say that it appears like a flow, right? It's like appear like a vortex, right? If you think about it, this is very beautiful example where you can see that human bodies are actually moving like a vortex structure. So each of these human body can be considered as the fluid molecule, okay, or fluid particle. And that's how. So now what I'm asking you, that you look at this example and you look at this video. Okay, everyone can see this thing, object moving, right? So what is the major difference in these two? Sorry? Okay, yeah. Let's not. Let's treat them very primitive objects and not go there. So in terms of structure, so since we are talking about patterns, so that's why that was the question. But you are right, of course, that is a difference. But if you think about in terms of structure, so here you can see that structures are almost, the moving objects are of the order of the system size itself, right? Whereas in these cases, the objects which are moving, those are of the scales which are smaller than the system size. Okay, so if you recall, the similar thing you had also seen when you had sperms, right? So you could see that the structure which was forming was going to be much smaller than the system size. Whereas if you think about these objects, your system size, your structure is going to be of the order of the system size itself. And if you recall the equation that we solved, the tonal 2 equation in earlier case, you see that there is coarsening that was happening. With time, the structures were growing. And if you wait for long enough, you will see that your structure is going to be of the order of system size. Okay. So now the question is, if you solve those equations and at the end, if you are going to get a structure which is going to be of the order of the system size itself, then how do you explain these systems? How do you explain the systems where you have bacteria which is moving around, or where you have sperm which is moving around, and when they form the structures which are of the order of smaller than the system size and greater than the individual size? So these are major scale structures. So how do we explain that? Okay, so that means that it needs a modification to the equations. Okay, and so basically these guys, like so basically this experiment was done in the group of he's the first author, Wenchink et al. Raymond Goldstein was involved. I'm not able to recall the I think Stocker. Julia Yeoman is the one. Julia Yeoman. Raymond Stocker was also involved, or no? Raymond Stocker, Raymond Goldstein, and Julia Yeoman. Yeah, Julia Yeoman is involved, right? I get always confused between Raymond Goldstein. So Raymond Goldstein is the one who did the modeling part, and Julia Yeoman is also a theorist, but she was, I think, the lead author in that one. Yes. Okay. Now, before we go to the equation modification in the equation, let me show you few more examples. So of course, now the phenomena itself, the video that we have seen, it is going to be very different. When you have the structures which are of the order of the system size, usually you say that it indicates that there is going to be herding, flocking, or swarming kind of behavior. But then the behavior that we noticed for the bacteria or for the sperm, that we are going to call as bacterial turbulence. Okay, because the structures which are going to appear, they are going to be of the length scale which are smaller than the system size, but of course greater than the individual microscopic level. Okay, so you can see in all these structures, all these systems, the structures are intermediate size, mesoscale. This is again for the bacterial turbulence. This is from the you take the bacterial field, you convert it to vorticity field, and you can see that these structures are mesoscalic structure, and these are long-lived structures. Long-lived structures, I mean the size of the structure remains more or less same over the period of time. Okay, and these are from different model. That's what they have shown. Now this is.
Do we have vortex stretching?
Oh, we don't have vortex stretching. Yes, you're right. Yeah, these are fairly long-lived. So how could so in that spirit?
Forces.
Yes. Other forces here, but again, in terms of patterns, these systems are still not very well explored. Okay, whether the patterns are going to be coherent or not. So that's the reason I want you to give an idea that, okay, here are certain examples. For example, if you think about 2D turbulence and all, we know very well, it is very well established that the structures are going to be coherent. It is a well-known phenomena since 70s, 80s. People know that it is going to be there. But what about these new systems? Okay, for example, viscoelastic fluid flow is there, but it has still not been very well established whether the structures are coherent or not. Similarly for the thinning flow, similarly for the active system. So here what we'll try to do, what I'm trying to motivate you, I want to tell you that, you know, these are the systems which are unexplored, and what you are going to learn in the course, you can try to explore for these systems, because I know many of you are working on different problems, and these could be one class of those problems. Okay. Fine. Now, if you think about bacterial, so this is another example of bacterial suspension. Here, what has been done, this is the velocity magnitude, this is not the vorticity field, and you can see structures are not very clearly visible, but the spot, the size of the spot, again, you can see that it is mesoscale, right?
So this image is at the lower concentration.
Yeah, this is at the.
So maybe actually this one, like the characteristics structures are not appeared at the.
No, I will go to that. I am coming to that. So there is a reason why I'm starting it in this. Thank you. Okay. So you can see that the structures are usually of the mesoscale size, and this has been the story till 2020 or something like that. Okay, now let's try to understand what modification you need to do in the equations if you want to actually understand it. So again, in the same paper, Vencek et al., the group of Yeoman and Goldstein and all, Jorn Dunkel was also, Jorn Dunkel was the one who did the modeling, right? So basically what you do, you take your Toner 2 equation and you do a modification at these terms. So you remember here so here these terms were different. If you recall your incompressible Toner 2, you had terms, okay, this would be capital, by the way, capital gamma 0, gamma 2, but doesn't matter. So basically here you had only viscous term, but what we have done here, we have changed the sign here, and we are saying that now viscosity is going to inject energy in the system, and then another higher order term is going to dissipate the energy in the system. So basically using this beta u cube and gamma 2 Laplacian or second Laplacian term in the system is going to dissipate energy at the largest and smallest length scale, and alpha u and the anti-viscous term is going to inject energy in the system. So now you are injecting energy from the 2 points. Okay, and the reason why this term was added, and this equation, by the way, it's very commonly known as now Toner 2 Swift-Hohenberg equation, because this additional term is coming from the Swift-Hohenberg kind of model, okay, which was very popular in condensed matter theory, where you can use this kind of equations to describe different kind of patterns. Okay. Now also, if you think about this equation, so this immediately gives you a length scale in the system, which was missing before. If you think about Toner 2 equation, there was no inherent length scale that was coming into picture. So the only inherent length scale that we had in the system was the box size itself. And that's the reason the structures that we had were always going to be of the order of the system size. But now, since we are introducing a length scale in the system by hand, it means that this length scale is going to come into picture. And what you will do, by taking the ratio of these two, you are going to get a length scale. And these structures are going to be of the order of those length scales. Okay, so again, if you solve these equations, this is the kind of structure you are going to get. So of course, when you are at the low activity regime, you can see that you have many nice small mesoscalic structures, and again, these structures are much bigger than the organism that we have in hand. But then something interesting happens when you increase activity. You can see that there are some some large scale structures also start to appear into the picture. Okay, so this is one observation when you start to increase the activity. Okay, and of course this work is done by Siddhartha at Kanpur. Okay, now
I have this doubt in this model.
Yes.
So how can we physically think about this, that the viscosity is as an energy injection, right? That part.
No, so I will tell you a story. So when I was writing Navier-Stokes equation once, then Matthias said, this viscosity is an empirical thing. There is no exact form of it. So you can always define what way you want to dissipate energy. Okay, so here what we are trying to say, that the viscosity or the energy dissipation that is going to happen at small length scale. So basically we want to mimic how the viscosity is going to dissipate, or at the molecular level how the energy is going to be dissipated. There's no rule that it should dissipate in the energy in a certain way. There is no rule that it should always dissipate its energy using this Laplacian form. You can say that I can define a term where it is going to dissipate energy with a fourth order term or by Laplacian term. Okay, so that's the motivation. Since you have this liberty, you can do that. So you have added the dissipation term. Now you want to inject energy. So once you have set the dissipation to take into account a viscous, so this is now more or less like a viscous term. Okay, you can say that this is equivalent to viscosity. Now you want to add a forcing that is happening at a length scale which are definitely greater than the viscous or dissipation length scale, right? So that's how you do it. You add a bi-Laplacian, and then if you go to Fourier space, you can easily see that what length scale it is going to correspond to. Okay, so that's the idea. So you cannot
What's the question?
So the question is that what is the meaning of negative viscosity?
So I think I agree with what Anupam said. Maybe, so the way I think about it is that, these equations are not now first principles equations. So basically this is just telling you that there is a force that is, so when you write basically the stress in the Navier-Stokes, this is basically, and then you take the divergence of the stress, that will give you, let's say, the stress, which is, viscosity times rate of strain times.
Right.
When you take the divergence, you get, viscosity times Laplacian of u. But now think about having another force that tells you, okay, I have a force that is proportional to relative velocity between me and my neighbors. So these guys are not really a piece of fluid. This is just an abstraction, it's a modeling assumption. So you can, it's fine to put a different coefficient. So you think of this as a viscosity, that's good, but not really, right? Because this is just a force that is proportional to a stress that is proportional to gradients in velocity. And then for this particular system, this is the, if you pick parameters in a particular way, this is what best reproduces the observation. It's not really, that's the way.
So from the first principle, it is impossible. So you can already see, okay, so not say it out loud, but this is a patch. You have two equations, you have patched them, right? So you have like this Swift-Hohenberg equation, which is separate equation. You have a Toner 2 equation. You patch them, and then you see what you're going to do. And of course, you can, at the end, if you are able to describe the experimental observations, you're like, yeah, this should be the equation which should be able to describe. And of course, as a physicist, we can always justify which term is doing what and how it is going to represent the actual physics. Okay, so that's the idea. Yeah, any more questions here with the equation? Okay, fine. So now, but the interesting thing is that if you extract a length scale, so you all can see that one can extract a length scale using this gamma 0 and gamma 2, right? And the length scale of each system is going to be of the order of the length scale that you're going to get. So this vortex size will be of the order of the length scale that you're going to get from gamma 0 and gamma 2. Okay. Now, if you think about these length scales are going to be much larger. Then means you can already see that this is much greater than these length scales, right, in the system. So what is happening? So okay, one thing I did not define, I'm saying that increase activity. So there are n number of ways you can increase activity, but in this system, you're only controlling alpha, and then you're seeing that how your system is going to respond, how your system is behaving. You can also play with the strength of gamma 0. You can also play with the strength of lambda 0, and in that way you can control your activity. Okay, how active your system is going to be. Okay, but here in this problem, alpha is being used as a knob, as a control parameter to tune your activity. Okay, fine. Now the similar kind of simulations and have been done. This is done by the group of Stefano Musacchio at Torino, and what they find that this is a different geometry. The earlier one, the simulation was done in a periodic box. Here the simulation is being done on a disk, and you can see again the structures with this when you have a smaller activity are going to be much smaller, and again the length scale is going to correspond to the length scale that we get from gamma 0 and gamma 2, whereas if you keep on increasing activity, again you are increasing your activity through alpha, and you can see that the structures which are going to appear are going to be much greater. Okay, and again in their finding, what they realize that if you keep on increasing activity, basically your vortex size hits the system size immediately. Okay, that's what their finding is. Now this is the experiment I think you were referring to, right? So now if you look at the experiment done by the group of Shiva, there what they did, they increased the bacterial concentration, and they're saying that bacterial concentration is going to be directly proportional to activity, and if you do that, you can again start to see that there is appearance of large scale structure. So here velocity magnitude has been plotted. You can see that at smaller bacterial concentration, the structures are, so again you can see that what is the reason why it appears very blue, because this concentration is small, so corresponding velocities are going to be weaker. But if you can you can try to look at it carefully, you can see that there are structures which are going to be very small. But if you focus on the right hand side where bacterial concentration is high, which means that the activity is large, the size of these structures are going to be large. Okay, so you can already see that in experiments that there has been some findings, there is some degree of correspondence. If you increase activity, you can see that the sizes start to increase. Okay, fine. So also what one can find, so what has been done by Kirti, that she took the same equations and then she tried to increase activity, and she has done a really high result simulation, and what she finds that if you zoom in, so this is the case when your activity is small, where alpha is -1. On the right hand side, you have a case where activity is large, where alpha is -9, and you can see that the structures appear to be very different. Okay, and if you focus on these structures, for the same box size, you can see, and by the way, this box size is almost 25 times greater than these small length scales. Okay, so you can see that it is pretty big. Okay, so up to 25 length scale, if you see that, you see that it is just a single structure. So now, so for this system, what we would like to, or what anyone can ask, what happens to these structures? Are they coherent? And so the same question that one should ask for the simple Navier-Stokes equation, one can try to ask these questions for these systems as well. Okay. So the idea is that whatever you are going to learn, you can try to implement for different system. That's the overall goal. And you can see that depending on what system you are choosing, your structures are going to be very different. For example, your viscoelasticity, if you bring in viscoelasticity, you can see that your structures are going to be smaller. If you bring in thinning fluid, you can see that your energy dissipation is going to be weaker, and that may lead to maybe smaller structure, but your structures could be long-lived. Okay. Similarly for viscoelasticity, because viscoelasticity is again related to drag reduction. Okay, so there is going to be a lot of it's going to be a smooth flow. So again, your chances are that your vertical structures may be long-lived. So how these things are going to get affected, and these examples are pretty common in nature. For example, we know that this is example of like bacteria, which is quite ubiquitous in the system. We have also seen that the shear thinning or shear thickening fluid and viscoelastic fluids are also very common in the nature. So what happens to these systems? Okay, so these are the questions that one should ask.
Can I ask one question? So if we just look at the equation, let's say the one before.
Right.
Okay, so you say, okay, it's easy to see that there is a new length scale.
Right.
But just looking at the equations without simulating them, is there a way to guess?
No, so once you see the results, then you can justify. So
but then, also if you have an a posteriori recipe. Right. But what is the recipe? So
basically what happens if this gamma 0 starts to dominate, it means that your small scale activity is going to dominate. So if you keep your alpha fixed and you keep on increasing gamma 0, what you will see that small scale structures will start to become more and more dominant.
So that means basically, so if I extract the length scale, which is square root of gamma 0 by gamma 2.
Right, yeah, exactly.
I don't remember. Yeah.
So it's
gamma 0 by gamma 2.
Square root by gamma 0, square root of gamma 0 by gamma 2. Yeah. So that will be one length scale, and if gamma 0 dominates, it is going to be a dominant length scale. But suppose if you keep on increasing weight for this, then of course this is going to dominate over. So this is like a disturbance at the small length scale, and this is like a parameter which is trying to correlate the structure or homogenize the structure, which means it is trying to lead towards the flocking. Okay. By the way, all these structures means it is not very clear in this image, but if you look at the images that I have shown later, you can see they represent a flocking state. Okay, so basically when you have very large structure, it is very similar to what you observe in herding or flocking or any such thing. Okay, and that is also can be connected to the ordered state. So if you start looking at how your velocity PDF and other such things are going to look like, it will start to go back to what you observe in Vichek or Toner 2 kind of setup. So by the way, I did not mention, but Vichek model is the one that is able to explain the herding, flocking and other behavior. Okay, right. Yes, so to address your question, Matthias. So basically these disturbances will try to inject energy at smaller length scale. So that's where it is going to dominate. But if you keep on increasing alpha, this will dominate over these two guys. So flocking will try to dominate. Now what is happening in these states, and actually this becomes much clearer in this image, you can see that there is a mixture of state, right? So you have states which are trying to flock. Okay, these structures flock or herd when alpha starts to dominate, but then you also have structures which is going to be be chaotic, which means these structures are, so length scale of these structures, these small structures are exactly same as the length scale of these guys, because what you have both of them are present now. But if you keep on increasing alpha, you will see that flocking state will start to dominate more and more. Okay, so basically this area will start to grow. So the area that is, so herd size will start to increase. So if you keep on increasing your alpha value, it means that the Toner 2 kind of behavior is going to dominate, which means the herd kind of behavior is going to dominate, and then you see that there is going to be larger and larger structure. Okay, and the same thing can be seen even if you look at the correlation length and all. So actually one can define a critical number here. One can also define order parameter and all such thing, and you can check. So there are time scales involved in these two systems. So basically if you go back here, so alpha gives you inverse of one time scale, and then if you take a combination of these two, gamma 0 and gamma 2, that is also going to give you a time scale. Okay, so basically gamma 0 is the dimension is 1 by time, time into time divided by length squared, and this is also time divided by length squared, and if, time divided by length to the power 4. And if you do dimensional, means if you can extract a time scale. So basically there are two time scales involved in this system. Now which time scale dominates, that is going to define whether you are going to have a smaller length scale or larger length scale. Okay.
So is it true? So if I look at this equation, I think about alpha u as injection of energy at small scale.
No, alpha u is injection at large scale. That's how so it is happening at all length scale, but which energy will dominate if it is going to be a function of u, it is only it is always the large length scale energies will dominate over small, because so it is linear with u, right? So if you are going to add, so of course small length scale energies will not contribute much. It is only the large length scale energies that will contribute much. But if you if you think about this guy, since there is a Laplacian, which means k squared comes into picture, so immediately this is going to dominate only at small length scale. So this dominates at small length scale, and this dominates at all length scale, but the major contribution comes only from the large length scales. Okay, that's how. Yes, please.
If I think about from the experiments, so the only length scale we have is the bacterial length scale.
Right.
It is injecting energy.
Right.
So how one can think about those two small?
Okay, so it is a tough question. As I said, that all these equations, what you try to do, you try to see that which parameter gives the best result. It is very difficult to do a mapping. It is always an empirical mapping. You do your experiments, you do the simulation, and then you try to match the expression and say, this parameter for these set of parameters and these structures, they appear to be same. So, this is what it should correspond to. That's what people have been doing. For example, if you think about this, this experiment. So, here the bacteria is exactly same, right? You just increase the concentration. So what I see, if you are increasing concentration, since there is going to be crowding, and if you remember Vichek model, right? If you increase density, the possibility of herding is going to go up, right? So that's how I see that if you are increasing, density, it means the herding behavior is going to dominate, which means that it should directly affect alpha, because alpha is directly connected to the flocking nature of the system.
Is it like the second large length scale is coming because of this, like this flocking?
Yes. The second large length scale is coming due to the flocking behavior of the system. Okay. Fine. Any questions? Okay. Okay. Now, what I want to do, so there is another kind of active fluid, which is active pneumatic flow model. So what is the difference between pneumatic and active polar fluid? So in polar fluid, you have a clear differentiation between head and tail. But if you think about pneumatic flow, there is no differentiation in what is head and tail. So for example,
Sorry, can I ask one more question?
Yeah, please.
So basically, if I compare this with the active pneumatic equations.
Oh, that I find pneumatic equation too complex.
No, but I mean, this is something conceptually different. At least maybe I'm misunderstanding. But there, the injection of energy is always at small scale, at the elementary unit scale, because basically the injection of energy enters into the divergence of the active stress. Exactly, right there. And that divergence of active stress is going to have two gradients. This is some sort of a Laplacian of, because you see basically, so you have sigma.
Yeah, sigma can be broken into two parts. One is the elastic contribution, the other one is active stress.
So let's say so that sigma is going to bring you a 1K. When you
Let's do one thing, because anyways I have to cover it. So let me show the equation, then we can discuss. Okay. Sorry. Okay. So the next topic is pneumatic flow model. So here, what you are seeing here, these are nothing but beads, rods, and they have been kept on a vibrating bed. Okay. So basically, what happens if you start to vibrate it, you will see. So how are these? So basically, if you think about a rod, if you put it on any surface, it is not active in nature, right? It will not move. But if you start to shake it, you will see that it is going to move around, right? Because energy is being transferred through friction. Okay, either you vibrate vertically or horizontally. In that way, it is going to transfer energy, and that's how the system, these rods are going to get activity of the system. Now, what happens is a famous experiment done by the group of Ramaswamy, Sriram Ramaswamy, and basically what they find that they start to show ordered structure. Okay, so you can see that all these beats tend to align with each other, and again it is going to be a function of what is the density, what is the activity, and all such things come into picture. We are not going to get into detail, but you can see that there is going to be an ordering in the system. And now also, if you look at the structures are going to be much bigger than these individual agents itself. By individual agents, I mean the rods itself. Okay. Now on the left hand side, we have example of microtubules, and basically microtubules are nothing but, if you take your cells in the cytoplasm, you are going to have these microtubules. Okay, and these are like long fibers. Okay, now how these long fibers move around, and they are active in nature, by the way. Okay, the way it is designed, let's not go into detail, but they are active. So basically you consider fibers which are active in nature. Now how the dynamics is going to look like. Again, if you think about fiber, there is no head-tail asymmetry. So even for these rods, there is no head-tail asymmetry. Even for these microtubules, there is no head-tail asymmetry. Now if you take these systems and if you start looking at how the dynamics is going to be, you can again see that the patterns start to emerge. Okay, and these patterns are again going to be much greater than the small rod or fiber size, and these are again scale in nature. Okay. Also, there are some other associated things, like there is a plus half, minus half defect, that we are not going to look into detail, because the dynamics will not only be driven by the hydrodynamic interaction, but the topological defect also comes into picture, and that leads to other kind of interaction. Okay, but the important thing, that the key takeaway should be here, that for these systems also you are going to get structure, but what is the origin of structure is going to be very different. And can we again try to ask the same question: what happens to these structures, these patterns? Okay. Now the equations which Mattia is interested in. So this is the general equation that you use to describe. So there are many ways of writing it. The one I have chosen is taken from Luca Giommi's PRX paper 2015, and this is how he has described. So you have like incompressibility, you have Navier-Stokes equation. If you think about the stress that is being added to, so this equation is very similar to what you have seen for the viscoelastic flows, right? So you have Navier-Stokes equation, and then you are going to have an additional stress that is going to contribute to the forces in the system, right? And in what we had for the viscoelastic system, we said what we are going to do, we are going to look at the strain tensor, and then from there we are going to say that strain tensor is directly related to, you know, stresses, and if you take a divergence of it, you are going to get the force. So that's what is being done here. Now in this case, there will be two contributions. If you think about, so these pneumatic guys, means if there are rods, so they will have a natural elasticity, right? If you put many of them aligned and if you try to move them apart, there is going to be a natural elasticity that comes into picture. So if you have only pneumatic kind of system, you're always going to have this elastic contribution. That is always going to be there. Now on top of that, we are trying to mimic the activity that comes to the system, okay? So this stress is going to, so only due to pneumatic nature, anyways the dynamics is going to be different. Okay, very similar to what you had for the viscoelastic flows. But since these guys are active, there is going to be an additional contribution to activity. Okay, now what one can do, one can define an order parameter for these system. So here Ni is nothing but a director field. So when you have these rods, what you can do a coarse graining, and you can try to define what is going to be the a director field for that. And what you can do, you can try to write a tensor field which is going to have this form Qij, and this is known as you know, the pneumatic order tensor field. Okay, and the dynamics, what you have to do now, you have to in terms of field, you have to write down an equation for Qij, and it is going to have this form where you will have like S that comes from the ordering. This is the you know, strain tensor. This is like how Q is going to get affected due to the vertical nature of the flow, and then you are going to have something like molecular tensor. This gamma is I think this gamma is going to be a time scale, and that's how the system is going to relax. Hij is going to have a form which comes directly, the stress comes directly from the free energy formulation. So what one can do, one can define a Landau-Design's free energy, and this is going to have this form. So let's not worry about all these details, but this is how, so that's why I said that I find these equations little too involved. But the important thing is that how your Navier-Stokes equation is going to get modified. You will have a stress term where you will have an elastic contribution, you will have an active contribution, and how things are going to get affected. Now I think Mattia has a question like this activity, it is only going to act at small length scale, right? Means at least the way the forms are written, that's how it should be. Yeah, now.
Well, I mean, yeah. So the intuition is that because you have this basically little. I mean, let's say even in the liquid crystals, you have these little sliding bundles of you know, of microtubules.
Right. Right.
And I was trying to understand. So and you know, if we go to Fourier space, basically right, there's gonna be a gradient there. So at least you're gonna hit, you know, a gradient of alpha Q. Alpha is constant, so that's fine, but you're gonna still have, you know, gradients of Q.
No, so basically for corresponding to this term, right? Yeah. So I think you will have a k squared kind of contribution. Okay, I
don't know where is coming the other k, because one k is from the gradient. I don't know where the other k should come. It's not really a Laplacian.
Yeah, you're right. So one case we can see immediately. Now this Qij, alpha Qij,
because
which is comes
just
from
n and the nematic order parameters. So those are just. So the thing is that conceptually these two equations are a little bit different.
It's very
where you are inserting the energy.
Right.
Although they are trying to model the same thing.
No, but the thing is that they're trying to describe the same things, but in some sense you are right.
Yeah. I mean,
but I. Yeah.
Of course, here you have much less degrees of freedom in terms of you know, this alpha 0, alpha 1.
Right. Okay. Yeah, that I agree. So here the only control parameter, the only parameter that you tune is alpha, and again based on what is the sign of alpha, you can see that it is going to be a pusher, puller, or contractile or extensile
You have a little bit of parameters in the free energy, but you know,
But this one can, I don't know, but I think one can accidentally find. But this is, of course, the equations are more complex, but these things are already well established. It is from Dizin's time we know that what it is going to be. So the only thing that was added extra was, you said, you know, what I'm going to do, I'm going to add an additional activity, and this activity is going to be a function of this cinematic order. End of story. Okay. And it is so okay, now if you solve these equations, what you are going to see, structures which are, so this is top left is experiment, these are simulations. So what has been done in the background, vorticity field has been plotted, and then you have contours around it, streamlined contours that you have plotted yesterday, and you can see again the structures are going to be much smaller than the system size itself, and one can try to look at these structures qualitatively, and they are going to appear to be similar, not precisely, but a qualitative matching is there. I think quantitative comparison have also been done. These equations have been used quite extensively. Okay, now here the defects and other things has also been quantified, but one thing that you will notice that, so can one tell, like if you look at this vorticity field and the vorticity field that you have seen earlier for the active or the Navier-Stokes equation, can you see any major difference? Like, do they appear more stretched here, more elongated vertical structures in these cases, or you don't see any? No, to you it appears okay. Yeah, so here it means they appear to be more elongated. Okay, compared to if you think about active or means polar system or Navier-Stokes, but again that comes from the equations that you are solving. Okay, so now what I will do, I will stop here, and what we'll try to do, the next topic would be what we are going to, this is what I wanted to cover in the second half, that Lagrangian tracking and statistics, because this is something important that you are going to use. So how to do, if you have a fluid flow, how to do Lagrangian tracking, that's a question that you are going to address in the second half today. But before we go there, let's try to quickly revisit what do we mean by Lagrangian tracking. So like if you think about these pollutant dispersion or cloud formation or swimming of microorganism or mixing process in industry, in all these cases you can see that these guys, like if you think about, let's focus on this pollutant dispersion. What are these? These are aerosols which are moving around, moving in a atmosphere. Atmosphere is general, there will be some degree of turbulence, and these guys are moving around, right? Now the dynamics of these aerosols are going to be very different from what you will have for from the Eulerian field, from Eulerian. So I will go there, but if you want to understand this, like pollutant dispersion or cloud formation or any of these guys, what you have to do, you have to consider that a Lagrangian approach. Okay, if you want to understand it in a better way. So what do I mean by Lagrangian or Eulerian statistics? So when you solve so the equation that we have seen, Navier-Stokes equation, when you solve them on grid, and so suppose, let me erase this first. So suppose this is the domain of interest where you want to understand what is happening here, and suppose if you are at a point, you are an observer, you sit there and then you try to do the measurement, means how the flow around it is moving, of course. So flow will, since it is not in steady state, its value is changing in space and time. So if you if the observer is fixed in space and if you do the measurement, then you will say that whatever measurements you are doing, that is going to be Eulerian measurement, right? But if you start to move along with your fluid particle, then you will see that that observation is going to be a Lagrangian observation. Okay, so that's what I mean by that. So if you think about the pollutants which are moving in the aerosol, if you really want to understand the dynamics of it, you have to move around the pollutant, okay, or, along with the aerosol, okay, then only you will be able to understand what is the dynamics of this, okay. And to do this, what you have to do if you want to solve this to simulate these systems, you have to solve Navier-Stokes equation to mimic the flow around these particles, and then you have to advect these particles in the flow, okay. And for that, what you will do, you will say that I will solve Navier-Stokes equation on a grid, okay. So basically, at each of these grid points, you're solving Navier-Stokes equation, right? And in that way, you have information of the velocity field and pressure field at all these points, right? But if you want to have the information of these, tracks, what you will be needing the information of velocity field at the intermediate points, okay? So that's the major difference in these guys, the approach. So this is going to be the challenge. So that's what. So this is what you are going to do in the second half. The information will be given on Eulerian grid that you have already seen yesterday. Now for this, what you have to do, you have to seed certain particles, and then you have to see how this particle is going to get advected in the flow, okay? And that's what is going to be Lagrangian tracking. But before we go there, let's see why it is important. So in Eulerian field, you look at the field. For the Eulerian kind of description, you have velocity field which is given in space, and then you try to look for the dynamics of it. Whereas if you have like Lagrangian kind of description, then you will say that you will focus on the individual fluid particle, and then you will try to see how these fluid particles are moving around, okay. That's the major difference in the approach. This becomes important because in the early times, especially from the turbulence community, what people wanted to understand how the turbulence, is there a universality in turbulence, okay. So what you usually do, if you think about, there is a flow which is going from flow past a cylinder or any such thing, or flow past a column that we had seen yesterday, which generates a turbulent fluid flow. In those limits, in those cases, what you will do, you may put like few sensors there, okay. And what you will do with these sensors, you will fix these sensors in space, and then you will do the measurements there, okay. Through those sensors, you will get the velocity field. So now that information is going to be your Eulerian Eulerian information, right? So basically, this is what. So this is one way of doing it. The other way of doing the measurement, what you do, you put some floaters or some tracer particles. I'll be showing some images, and those tracer particles will be moving around, and then you do the tracking. Now, the thing is that if you do all the scaling and all the calculation to get structure function, structure function is nothing but if you look at the velocity increment, and then you try to see how it is changing as a function of distance, that's going to give you the information of structure function. Okay.
I have a question on that.
Oh, okay. Can
we unmute or?
Yeah, can you? I can come.
This one ask him to unmute.
Okay. Okay. Hi, Soumitra. Can you?
Hi, Soumitra. Yeah, I can hear you. Can you hear me?
Yes, I can.
Yes.
Yes.
So you have introduced different flow.
So, is there a mic anywhere? I cannot hear the question.
Yeah, because you have this microphone and this microphone. So just mute the one from your computer.
No, but I suppose if I just switch on this guy, right? I've kept my mic off,
Oh, the mic is off.
but the speakers are on. So if I start to speak, there is going to be.
Is anyone else? Try now.
Hi, Soumitra, can you hear me? Soumitra, can you hear me?
Hello.
Yeah, now it is fine. So, okay. Yeah, please ask. Can
you put your
Hello, can you hear me?
yeah, Soumitra, I can hear you.
Okay. There is some echo. I will write, somebody will read, and then you can answer actually. So I cannot talk properly. There is an echo.
Yeah, go ahead. I think it should be fine now.
Okay, fine. Yeah, so so you introduce all the flows. Thank you for that. But whenever you are introducing the flow, you are mentioning always mentioning two things. One is that depending on the condition, let's say in the Navier-Stokes case for energy injection scale, depending on the energy injection scale, the structure can be very different.
Right.
And also in the active case, depending on the value of alpha, the structure can be very different. And also in the pneumatic case, depending on the activity, the structure can be very different, right? So in terms of coherent structure, so these are model, and we have some idea from the model, but in experimental data we don't have what is the time scale, or you are mentioning one word always that structure has to be long lived. So now the question is, if I am looking at a experimental data, then should I scan to get the Lagrangian coherent structure? Should I scan for all time, or how do I decide? Because they are how can I get that? What is long? How can I get long lived idea?
So maybe Mattia can answer this because he is the guy.
So
Can you hear, Soumitra? Can you hear?
Yeah, I can hear. Yeah.
So basically, you scan for increasing time intervals, and this is gonna reveal what time scales the structure form, disappear, if they keep existing. So that's the way to look at them. So for instance, if you run it for increasing time interval, let's say time interval 5 units, you get these structures. 10 units, you get these structures. Maybe they get bigger, but maybe at 50 units, you lose them. This is going to tell you precisely the nature or the history or the dynamics of the structure formation and disappearance. So you really have to explore different times. Or you can ask, do they exist for this time interval I'm interested in? And then you do the calculation for that time interval, and then you're done. They're either there or not. Is that kind of clear?
Soumitra, is that clear? So basically what I understand, like you look at the Lyapunov exponent, right?
Yeah,
and then you see that how long they are going to live, means whether they are going to stay there for that time.
Let's say you said that sometimes the vortex will dissipate, right? Depending on, so it will be certain time, it will exist for certain time, and then it will dissipate. Now, if my total time is after dissipation, then should I get that as a coherent structure or not? That's the question.
Well,
so basically vortices has a certain lifetime.
Yeah.
So if I do the observation for more than that lifetime, so should I get a coherent structure or not? Should I?
Usually not. So usually, if the motion becomes for a very long time completely, incoherent, you're gonna get an FTLE that is gonna be it's gonna really look like noise. So you can really think of this as the vorticity, right? So if you have big structures, the FTLE is also gonna have some sort of big structures. But if you have just very isotropic turbulence, you're gonna get very tiny little blobs, and you're gonna get something similar from the FTLE. It's gonna be very noisy, and no
structure. I think the structure will disappear. Yeah. So it is. So one way to look at it also, you can look at your Lyapunov exponent pattern in the flow in this space, and then from there you can try to see if the structure is there or not. So maybe one can also look at the correlation function for these, right? That can tell you that whether they are correlated or not. So I think one can also do that. So since as the name suggests, these are finite time things. So the finite time will depend on what system we are looking at. So how long we have to focus on the system, that is going to depend on the system itself. Okay.
So I really see this. So these dynamical system techniques, they are just a tool to explore what Lagrangian structures are there as you keep increasing the time interval of observation. So you really scan it, and this is going to tell you the answer.
Right.
But a priori we don't know, right? For experimental data, we don't know a priori. So we need to scan it for different time, or
Yeah. You have to do it, because again, any dynamical system that is time dependent, if you change the time interval, it's in principle it's just another dynamical system. They become the same only if you basically know it's periodic and you start scanning for multiple of the periods. But these are very unique cases. But in general, you don't really have simple trivial periodic systems. So they are just time dependent, and therefore, the more you crank the integration time, the more different is the system, and then this is one way to elucidate this distinction.
Okay. Okay, thank you.
Okay, thanks. Yeah, you can. Should we take a break now and then wait?
Yeah, as you want.
Yeah. So what I can do in the second half, I'll just, depending on whether you are looking at Eulerian data, which means that you are collecting the data from a given fixed positions, right? And or you are collecting the data where you are moving along with the flow. Accordingly, you will define a structure function. A structure function is basically you take velocity field at a given position r plus x, and then you take the velocity field at a given position x with a separation r, and then you take a dot product with r unit vector, and that quantity is going to give you the velocity increment, longitudinal velocity increment. And now if you look at the power of it, that we will call that. So suppose if you take pth power of this velocity increment, and if you do it an averaging over domain, you are going to get a pth order structure function. Okay. Now this is an important quantity, because this tells you whether your flow is like smooth, or whether there is going to be intermittency in the flow or not. Okay. So this kind of ideas become important in the turbulence community. So that is a very important quantity to look at. So when you have like Eulerian kind of structure, this becomes a lot easier, because you are fixed in space, and the reason comes from the fact that whenever in early days you did the measurements, you had the sensor that you put in the flow, right? And that's why these kind of quantities become important. So you'd like to see that, okay, if there are two sensors which are separated with a distance, and then how the velocity difference and how the space separation is going to be connected. And Kolmogorov proposed the theory that we know that how it should be done. Okay. Now, if you do the same thing for Lagrangian thing, so now the separation does not make sense, because you are tracking the same particle which is moving around. So what you will do, you will say, in place of separation, I will look at the time separation. Means in place of space separation, you will look at time separation. So you will say that now I will take the same particle. I will say that what is the velocity at time t plus tau, and what is the velocity at time t. I will look at its separation. I will take its power p, and then I will try to see how the dynamics is, means how it is going to be connected to the separation. Okay, that's how you define a Lagrangian equivalent of the structure function that you have for the Eulerian case. Okay, now these exponents p. So first of all, why do you think that velocity separation should be connected to distance? Should it be connected? That is the first question you should ask. So I said that it should be in this way, but what do you think? Should it be connected? So if there are 2 points, so basically you don't look for very large distances. Suppose you look at these 2 points, okay, and you look at velocity separation, and you look at this space separation, and then you are trying to connect. Okay, you want to see if there is any correlation. So it gives you a correlation, right? What happens to these things? Okay, so it tells you whether things are correlated or not. Okay, and how fast it is decaying, or how slow it is decaying. Okay, fine. Now So if you are talking about Eulerian structure function, you are going to get an exponent which is going to be, let's say, zeta p, and other case it is going to be zeta pl, and these exponents for the two cases where you have like Lagrangian equivalent and Eulerian equivalent is going to be different. In one case it is p by 3, which means that your this quantity s of p, which is equal to delta u, L, I think I need to check, yep, if you take only Lagrangian, see this is going to be delta r to the power p by 3 for the Eulerian case, and if you do for the Lagrangian case, okay, which is delta u this is going to be tau to the power p by 2. So you can see that the exponents are different. But the important thing that I want to mention here, that for the Lagrangian statistics, these exponents are much more sensitive. So this is the case, this will be the case when there is no intermittency, okay, in the flow. If there is intermittency in the case, then these exponents will start to deviate from these numbers. Okay, and that's what, and it is much easier to perceive if you have a Lagrangian data. So this is just to give you a motivation that why Lagrangian became such an important quantity, and how Lagrangian differs from the Eulerian thing. Okay, looking at the statistics for the Eulerian and Lagrangian are very different. Okay, now I will just, so this we had already seen, and this is how you do, this is how you do the tracking of Lagrangian particles. Okay, you have different polystyrene spheres of 25 micrometer, which is very small. If you put them in the flow, they will try to follow the streamlines. Of course, they will not be following exactly, but since they are very small, we can assume that they should be following. They will be like a tracer. And then what you do, you put them under laser sheet, you look at the reflection, and then from there you try to extract what is going to be the velocity field in the flow. Okay, and once you have that information, so this is again going to be a Lagrangian information, right? And then from there you try to get the information. Now what I will do, I will skip.
So what is p?
P is the power to the velocity. So which order, which moment we are looking at. Okay, so you can look at the linear, second, third. For third order structure function, we have an exact relationship that comes analytically. So in case of turbulence, there are very few results which are exact. Okay, and for third, I'm getting confused. Is it third order or second?
So these are
third order.
P goes from 1
to 1, 2, 3. You can go to even higher order. So also one thing that one should note that so this is the gradient in the difference in the velocity, right? If you go for higher and higher order values, then error in estimation of u will also going to grow. So that's why what people report, usually they go up to 4, 5, but not beyond that. If you go beyond that, then it becomes very challenging to trust your data, right? Whether the differences that you have created, is it actually going to be correct or not, accurate or not. Okay, so that's why people limit themselves only up to 4 or 5 minutes. Of course, even when I do, I also report up to 8, but the data cannot be trusted. It's a little tricky once you go to those numbers. Okay.
And these are you just pick any direction, right?
Yeah, you can pick any direction. Yeah.
And you shouldn't expect any differences.
Yeah. If this is for you. Okay. Important thing. This. All these ideas are valid for homogeneous isotropic turbulence. So there is no directional dependence. If there is a directional dependence, then the results are going to be different. Okay, but the thing is, yeah.
Does this bracket signify anything?
Average. You have taken this bracket, right? The angular brackets.
Yeah.
Average over space and time, both. Okay. So basically, this R you can fix like this, right? And then you can move your many such combination you can do in space at a given time, and then you can do an averaging over time also. So because this is very hard to get, like a power law is very challenging to get, right? So you have to do a lot of averaging. So that's what. Okay.
So if you do the same thing like in the Eulerian framework, like this time t. So
right.
You at some time t, and at the same position we look at the velocity at some later time. So is that also
No, so sorry, can you repeat your question?
just I have taken u r plus x minus ux.
Right.
So in this framework, if I just take u at t plus tau minus u at time t,
Right.
and I'm looking at the flow at some later time,
Right.
the same thing.
Okay.
So is that also giving some kind of signature?
So you're looking at a given fixed in space and time. So not autocorrelation, like autocorrelation in space in some means
Correlation over, right?
correlation over time, but fixed in space, right? So no, okay. Let me. I think for small scales it should be fine if Taylor means you should get something like.
What's the question?
So the question is that if you replace, like if you fix your x, okay, you fix your x, and what you do similar calculation even for the Eulerian field. So basically, you say that this is where I'm doing the measurement, right? Now what I'm going to do, I have a measurement at time t, and then I have a measurement at t plus tau. Now if you look at the difference and if you look at the power, is it going to be similar to what we get for the Lagrangian or no? I think it will not be like Lagrangian. I don't know. I don't have an answer.
Only if your system is algorithmic. So only if if you run it long enough, a trajectory is going to span all the space, and I think you're going to recover the same statistics. But I didn't do it.
I don't know. So here the thing is that when you are looking at ui at t plus tau and ui at time t, so there is a hidden information, like that ui at t plus tau is actually, it can be somewhere here, one point, and the other point could, let me use a different color. Okay, anyways, I will use a different symbol. So suppose you are somewhere here, ui at time t, and then after time t you are somewhere here, right? Now at these times the velocity of the particle, Lagrangian particle, is exactly same as the velocity of the Eulerian field, right? And here also the velocity of the Lagrangian particle at time t plus tau is exactly same as the velocity of the Eulerian field. So these are two separated points, right? But through correlation and all, this is how you are going to see. So I don't think that you are going to have an equivalence there. I don't know. I don't have an answer for that. Okay, but these are very different. Like what you are saying, you should see very different relationship there. Okay. Maybe if you use this Taylor-Frozen hypothesis, then one may try to say something that how should the space and time should be connected, and then you can use the similar idea, like then you will say that since we know that space and time are connected, and then you can use this r to the power zeta p to get an idea about how the exponent for the time is going to be. So, but if that hypothesis is valid, only in that limit we can say that. But otherwise, we will not be. So, Lagrangian and Eulerian is always going to be different. Okay. Fine. Yes.
But the correlation graph of velocity with respect to r and velocity with respect to time remains same. It decays.
Yeah, but the time scale could be different. Time scale. So that's what I'm saying, that if Frozen hypothesis is valid, Taylor's Frozen hypothesis, then they will decay. Then the relationships should be same. I expect them to be the same. Okay, but given the constraint, if the Taylor hypothesis, Taylor Frozen hypothesis is valid or not. Okay, where you connect your space and time, but it is not necessary that it will be valid. Okay. Okay, fine. Okay, now, okay, let me go to the question that we have. Okay, so the thing is that when these particles, they are moving in the a fluid flow, how will you model them? So basically it will have two components. One is background flow, or it could be turbulent or maybe non-turbulent flow, and then these particles or whatever we have not looked at, they are going to be being advected by this flow field, right? So you'll be solving two equations. One is going to be your Navier-Stokes equation, which you solve on a grid, right? And then these organisms, and if they are tracer, which means they are simply being advected by the flow, they are going to have exactly same velocity as the velocity of the fluid, right? So this is what you are going to have. Now to solve this, what you have to do, you will have a setup. So okay, here the question is how to find Vi when you solve Navier-Stokes equation. All the velocity fields are at the grid points, right? But these particles can be off grid, because even if you start a particle from somewhere here, right, what may happen at next step, it can be somewhere here, right? It is not necessarily it will go to the grid. So how do we tackle that, right? So for that we have to do a Lagrangian interpolation. So this is, let's say this is where you are starting, and after some time this is how the track is going to be. Okay, now what we do, since we know, okay, let me see. So suppose you want to know what is going to be your velocity at this point for the particle. You have the information of the velocity field at these 4 points. So what you can do an interpolation, a bilinear interpolation, and then you can try to get what is going to be the velocity, and that's what we do simply. Okay, since you know precisely how it is going to be, and this is what the expression that we are going to use. So suppose Q11, Q21, Q12, Q22 are 4 points, and you know the value of that function at those points. Then how will you get what is going to be the value of Q at point P? Okay, that's the question. So these 4 points are representing the grids that we have, 4 grids, and this is where the particle is, and we want to know what is going to be the value of this, whatever field we are interested in. It could be vorticity, velocity, pressure, whatever, what is going to be value here. So what you do, first you do simple linear interpolation, you get the values at these points R1 and R2, and once you have the information at R1 and R2, you do interpolation, and then you get what is going to be the value at P. Okay, so suppose Q1, I mean, these are the values, like Qij is the value at these 4 grid points. You do this simple interpolation. Suppose this point is X, it is going to be Q1 X2 minus X divided by X2. So this is a standard interpolation scheme which you all might have seen. Okay, and once you do that, you know exactly what is going to be the value of the field at point P. Okay, so this is what you are going to do in the afternoon. Okay, and let me I think I will stop here. Okay, thank you everyone. Mathieu, you can take over. Thank you.